Welcome everybody and hello to the course Crystal Engineering Chemistry Beyond the Molecule. In this video we will we start to talk about multi-component crystals. Multi-component crystals, well, this is not the typical task and the typical aim of crystallization. Well, what is crystallization? We use crystallization to purify anything. We have a mixture, or what we want to get is one single compound which crystallized from a mixture. So we have purified our compound. Now we have a solid, exactly our compounds inside, nothing more. Multi-component crystals, well, this is not the purification. What is it? So first, we have different types of multi-component crystals. We will talk a little bit about co-crystals today, the next time much more. We will talk about hydrates, solvates, also co-crystals, host gas compounds, and solid solutions. Strange class of multi-component crystals, solid and solution. Well, this is a contrast, yes, it's a conflict, solid and solution. Well, important is if you will get a multi-component crystals of the form AMBN, when we are talking about, this is very important, we will talk about the free energy. And the free energy of such a system must be lower than the free energy of the poor A or poor B. Otherwise, you never will get such multi-component crystals. Yeah. So once again we are talking about energy. So energy of such systems must be minimized. So at the background, how can you minimize enthalpy or entropy? Yeah. If you're looking for enthalpy, then what we see is that the interaction of AB is more favorite than the interaction of a system by its own, as AA or BB. AB is more favorite. Next thing is we have in the enthalpy-driven multi-component crystals, we have fixed and definite composition, the ratio. The ratio is always small values, have shown all small values, 1 to 1, 1 to 2, or 3 to 3, 2 to 3, something like this. Mostly 1, 1, 1, 2, not always. This was enthalpy. Entropy-driven multi-component crystals, what is going on? When we see it if we have molecules, if we have molecular crystals, with molecules which have similar, comparable size, shape, and chemical nature. And if you look to the ratio of such compounds, then you will see this is different. We have the values of M and N can be all values in the range between 0 and 1. Yes? Okay, this is talking about energy. What is the difference of singles and multi-component crystals? First look at this same. The same are the laws of crystal packing. The same are intermolecular interactions and the rules of general crystal packing, of crystal design. The difference in in this case, as I said, this is multi, we have two chemical compounds which are involved. That's the first point. And such result, the multi-component crystals differ in the behavior, the chemical and physical behavior to the single compounds. So solubility, for example, vapor pressure, yes, and sometimes the chemical nature differs in comparison to the single compound. And such compounds, because they have a different behavior, yes, molecular aggregation and so on, physical properties, solubilities, bioavailability and so on, and melting point, color and so on, where new compounds, different compounds in comparison to the single compound, where the own Cas number, that makes also sense. Okay, look to the first class, horse gas compounds. Well, from the molecular organic chemistry, we knew some things, morphs, or I don't know, whatever you want, cavities, whatever, a single molecule which has a cavity, very nicely, Okay, you can use this cavity to incorporate any gas. It is also possible such model in the case of supermolecules. In this case, this is one unit, and you see is interaction, intermolecular interaction between units forming this host. You can use this host, stabilized by intermolecular interactions, to incorporate gas, stabilized through non-covalent interaction. And talking about supermolecular host crystal engineering, well, there's always an optimization, understanding, a balance, you can say, between these non-covalent bonds. And, well, you can really use it. For example, here we have a compound as trimesic acid, you see it here, aromatic backbone and 3 carboxylic units, acid units here. Yes, this is here in the figure. What we can see is we have a framework here, we have a host, and well, to possibility we can use it to incorporate a gas, or we can use this to build up a big network. It's also possible. No? Well, now, as we have seen, we have a really stable host structure, and it's really comparable to zeolites. Zeolites, for example, and zeolites is very important. For example, heterogeneous catalysis and so on, purification and so on and so on. Always incorporating some gas. And you can sometimes use some, I would say, a little bit strange frameworks. Clatrates, so big network, it was built up by water, hydrates and solvates. And I think everybody heard about burning ice. Burning ice with clatrates, gas hydrates, where here in the ocean, in the sea, and we're often under the seafloor. Really, what you need is high pressure. See it here, really high pressure, and you need low temperature to form up this burning ice. Gas hydrates, gas which is stabilized, catched by water molecules. And well, with a really industrial interest, application interest, this was, I don't know, it was 1 or 2 years ago. No, 3 years ago, you see it here, it was an article, Japan and have extracted methane hydrate from the seafloor. This is a very important source for energy. Well, what is it? Let's have a look on the molecular structure, the molecular aggregation of gas hydrates. Well, this is gas hydrate. Yeah? This is the cage is formed by water. We have ice crystal, and inside is methane, for examples. You can, I will show you, you can substitute methane by some other alkanes. And depending on the alkane, you will get different cages. Have a look on mercury. Well, if you open mercury in a gas hydrate, you will find such a picture, such a file. First of all, what you see is a little bit strange because all oxygen is surrounded by 4 hydrogen, not 2. And if you look to the methane you see is not 4 hydrogen in the coordination sphere, there are sometimes more, 8. The background is what you have a look. If you look a little bit more in detail to the structure information, you see a space group very high symmetry. In such space group, which is all typical, very often that you have extremely high disorder of the molecules, disorder of the atoms. And well, this is the result. This means, for example, in this case here with oxygen, the hydrogen, 4 hydrogen, 2 hydrogen are disordered about 4 positions. On each position is half hydrogen. Okay? Well, now have a look on the crystal packing, or you can confirm with what we have seen on the slides before. We make packing, and first I think it's very nicely you can see here the carbon inside. Well, here you see the carbon inside here, the alkyne, which is surrounded by a lot of water. This is the first thing. I think this is possible to see. Well, much more better is if you click here on the short contact, wait some minutes or some seconds, depends on your computer, while you see it here. When you avoid all this hanging, delete them, and I think this is very nicely to see. Very nice you see is the host formed by water molecules, and the middle is always, or in the host as gas, you see your alkane, in this case methane. Okay, and what's similar what we have seen in mercury, and you can involve, if you want, methane, acetylene is possible. This is gas hydrate type 1, exactly this. And if you switch to ethane, for example, a propane, propane, or a mixture of methane and propane, when you get, for example, gas hydrate 2. Well, nice example how you can play in crystal engineering with molecules, how you can tune the molecular aggregation. Well, in general, solvates and hydrates, if you look at crystal structure database, then you will see that most of them, with the crystal structure, most of the moleculars are not solvated. Around about 80% are not solvated. And once again, talking about solvent, we are talking about entropy. If you look to the unsolvated crystal, this is a question of entropy factor. because entropy gain elimination of the solvent molecules from a nuclei to form up this unsolvated crystal structure. No? On the other side, in the case of a solvated crystal, when we have an enthalpy factor, because we have a strong interaction between the solute and the solvent. So the solvent is going inside the crystal structure. No? Well, in general, you will see in the crystal structure database most favorite solvent is water. This is 10 times more frequently found in the crystal structure than the second best, so on the top 10. And the second best is methanol. Okay. You can use solvents. I've shown you enthalpy driven, so we are talking about intermolecular interactions. Yes, intermolecular interaction versus general interesting in polar solvents. You can stabilize a crystal structure through directional interactions, very nicely. Have a look here, have a look here. Wait, going back. This is a molecular structure. And we see it here, we have a backbone, here aromatic backbone. We have a CO double bond here, CO double bond here. Well, and this compound is stabilized by interaction with water. Yeah, this is a water molecule, see it here. And if you expand here, you will see very nicely the water is between two molecules. You can say the two molecules are linked by water. So the crystal structure very nicely is stabilized by additional solvent between the two components. Methylene diantipyrine monohydrate. Or you can use solvents to stabilize the crystal structure by filling the voids, non-polar solvents. They fill the voids in cavity in the crystal packing. Once again, for example, here, if you look, going back, if you look here, for example, to this compound, this is a fullerene, is with substituted with CF3 substituents very nicely. Yeah. And what you see is additionally solvent with this toluene. And look at the packing. You see here in these voids, you can expand our packing. Hopefully, you can see something. And we will use here hopefully you can see it. Oh, maybe better to see it a little bit better. We switch here to ball and stick of a toluene, only with toluene. Or no, better to we make spaceful. So once you know, now we mark packing. When you see the voids, here, I think now it is possible to see. No? The voids of the crystal packing here are filled with toluene. No? Okay. So you can use polar solvents to stabilize the molecular structure. Or you can use non-polar solvents, filling the voids, and when you stabilize the crystal packing by itself. This was well. Now, last point in this video is talking about solid solution. As I said, this is a little bit strange, solid and solution. you will find, you could obtain sometimes solid solution if you crystallize components which are similar in the size and shape. No? Well, so we are talking about formation covered by gain and entropy. In the case of inorganic chemistry, this is well known, for example, bell, Glocken, Kirchenglocken, brass, bronze material, very often. In the case of organic chemistry, it is not so often seen. Less common, because a lot of these compounds are not really similar or comparable, and much more rarely are solid solution with 3 or more components in solid solution. I will show you 2 examples. One of them, or in general, erstmal have a look, the difference between co-crystal and solid solution. Yeah, I have 2 components here, and crystallized together, you will get a multicomponent crystal, in this case a co-crystal. You have stoichiometric, and this is well ordered. You see it's always the same order between the brown and the green balls components. It's always the same. You see the symmetry, the layers. For brown atoms in the sphere, near environment for green, and so on and so on. Okay. In the case of a solid solution, once again 2 components, well, this is the result. You have a random mixture. One component in the other component. This is the reason it's called solvent. You see it here. This is not the same environment of a blue one here in comparison, for example, with this one or this one here. It's not exactly the same. Once again, this is well ordered, and whereas you have a random mixture. Okay, this is the difference. And now at the end, this is one examples. So nicely, phenanthine and acridine. This is really similar. We talk about the crystal structure of arenes, aromatic compounds. There's a difference if you look, for example, of a carbon aromatic systems in comparison to a system in which one C is substituted by an hetero atom. But in this case, it doesn't matter if we have 1 substitution or 2 substitutions. No? And if we mix both together, we will get a solid solution. Another example we have talked about, if you look here, similar system, but in this case, we have the middle part is not aromatic. Rigid, on the left and right, aromatic system, and in the middle is a flexible part. Okay? The difference is only in this atom switching from amino to a methylene group. Okay, have a look in the space groups. So dihydroacridine and dihydroanthracene. In the case of dihydroacridine, you see it here, the values A, B, C, 7, 8, 5, 8, 10, 7. And we see in acridine 7, 7, 6, 2, 10, 7. You see comparable values. Also here the angle and the volume. A little bit enlarged, it makes sense because in this case we have 1 nitrogen inside. If you know going on, if we mix both components together, crystallize dihydroacridine with dihydroanthracene, when you will get a mixture, crystals, very nice, you see once again, similar, comparable cell constant. And it doesn't matter if you, for example, if you switch the ratio. For example, if you 0.1 of dihydroargidine and 0.9 of dihydroanthracene, or 0.2 to 0.8, anyway, whatever you want, no? Whatever you want, you will get always the same cell constants. And we have a very nice example for solid solutions. Well, okay, with this slide I end the first introduction, I would say, in multicomponent crystals. We will have a much more deeper look on co-crystal and how we can control the formation of co-crystals, how we can use some rules, some protocols to get the desired co-crystals or the multi-component co-crystals which we want.